Greetings and welcome back. I'd like to do some integration by geometry today. In particular, we're going to be doing definite integration because we're doing integrals that have numbers in the bounds. And I'm going to do it by geometry because sometimes the integrand is sufficiently simple geometrically that I can just look at a graph and use some geometric formulas for areas to compute the integral. So I want to start, we're going to do two problems, and I'm going to start with this one. We're going to do the integral from -2 to 3 of 2x plus 4 dx. I think it's important that I narrate these things because fundamentally all of the mathematical symbology that we have is intended to be narrated. And I think there's a lot of power that we take over the mathematics when we narrate it. So I'd encourage you, for every problem that you do, read it out loud to yourself. So I want to do this by geometry rather than using the power rule for integration on this polynomial function, which means that I'm going to start by drawing a plot of my curve. So we're going to need to go from -2 to 3. 1, 1, 2. Seems pretty decent to start here. That's going to be our x-axis. 2x plus 4. Let's draw the curve, and then we'll shade the area that we're interested in. 2x plus 4. 2x plus 4. This is a line. It is slope 2 and intercept 4. 1, 2, 3, 4. I think I'm gonna have to redraw this, don't you think? Because it's gonna go over 2 and up 1 and over 2 and up 1. Unless I made this be 2, 4, 6, and 8. I think that's what I should do. No, I'm going to start this video over. Hello, welcome back. I would like to do some integration by geometry today with you. In particular, we're going to be doing definite integration because I have numbers in the bounds right here. And I'm going to do it by geometry to demonstrate a real connection between integration, definite integration, as the area under the curve, and geometry as the study of as shape. So I would like to do this integral with you, where it's the integral from -2 to 3 of 2x plus 4 dx. I do think it's important that I narrate that, and that you, when you do problems in calculus, that you narrate what it is to yourself as a way of building up your confidence of speaking the language of calculus. If you're not narrating it to yourself, I think you're missing out on a key component of doing mathematics. Okay. So let's see here. So we're going to go from -2 to 3, and I've got a line that is has slope 2 and intercept 4. So how about I start by doing something like 1, 2, 3, 4, and let's see here, 1, 2, 3, 4. So that's going to be my x-axis. We're going to go 1, 2, 1, 2, 3. And now let's draw our integrand. The thing that we're integrating is the integrand. Passes through 4, and it goes over 1 unit and up 2. So I'm going to go 1, 2, 3, 4, 5, 6. I'm going to go over 1 unit and up 2, over a unit and up 2, over a unit and up 2. So that's above that. Here's my line. It's going to go over a unit and down 2, over a unit and down 2. So I've got the area underneath this curve is the shaded region, and it's just a triangle. So I can compute its area without having to do anything like the power rule for integration on this polynomial function. Not that that would be difficult. But I can do this by simple geometry by noting that this is a triangle with base 5 and with height, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And the area of a triangle is equal to 1/2 base times height, which is equal to 1/2 of 5 times 10 is equal to 25. That means that this integral here is equal to 25 just by doing geometry. Okay, cool. So let's turn our attention to a slightly different scenario, and that would be the drawing over here. And what I'd like you to note is that what I've drawn is a function that is given by two semicircles. So this is a circle, and this is a circle, the best I could possibly draw them. And the area underneath the curve, remember it's the SIGNED, the signed area under the curve, is given by the stuff in here, right? Okay. So the area underneath the curve from 0 to 3 on this is the area of a semicircle. And it's a semicircle of radius. Let's see here. If its diameter is 3, then its radius is 1.5. Right? So the distance there is the radius. The distance there is the radius. It's 1.5, which means that the area here is going to be pi times 1.5 squared over 2 because it's a semicircle. And so that works out to be 1.5 squared is 2.25. And that means I have 2.25 over 2 is 1.125 times pi. Okay, let's do the next one. I'm going to integrate from 3 to 8. Note that this area is entirely underneath the x-axis, and so it counts as negative, whereas this one counts as positive. The area is signed. The radius of this is half the diameter. The diameter is 5, which means that the radius is 2.5, or 5/2. Which means that the area of this, well, it's half the area of a circle, is pi times 5/2 squared. So this one here is equal to, let's see here. So if I expand this out, I'm going to have 25. I have 2 2's up here and another 2 down here. So that's 25 over 8. 25 over 8 times pi. Let's go ahead and rewrite this in terms of not a decimal here, because I don't want to start mixing decimals and fractions. In fact, I kind of questioned myself as I was writing this out here. I don't know why I decided to do things in terms of decimals, because it's easy to start like running into really long floating point numbers. And I'm going to try to stay in terms of fractions. So that's 3/2 right there. And 3/2 squared, 3/2, which means that this number here is 9 over 8 times pi. Okay. So this area counts positive. This area counts negative. We found each of them just by using the area formula for circles, semicircles. So when we go to the integral from 0 to 8, that's all of the area signedly. They're counting the SIGN sign of the areas. where stuff above counts positive and stuff below counts negative. So the integral from 0 to 8 of f of x dx is equal to the integral from 0 to 3 of f of x dx plus the integral from plus the integral from, ooh, I caught an error. I just found an error. Do you see the error I made when I did this one right here? 3 to 8 f of x dx. I missed my minus sign because this one's below the x-axis, so it counts negatively. Yes, the area of this semicircle was, in fact, 25 over 8, but because the area is underneath the axis, it counts negatively. Okay, so when I go and evaluate this, this is equal to 9/8 pi minus, because it's plus negative, 25/8 of pi, which is equal to, let's see here, 9 minus 25 is minus 16. So minus 2 pi. Yeah. I guess one thing that you should consider when you're doing indefinite integrals like this is think about if the function that you're integrating is related to some geometric shape that you know, which might let you avoid having to do the actual symbolic integration. You could just do geometry and invoke formulas. Or another use for this, because you might just be like, well, I could just do the power rule for integration. Fine. I have no problem with that. But one thing that you should consider is that you can estimate the values of integrals by using geometric primitives like triangles and squares and rectangles and circles and things like that, so that you can get like ballpark estimates for what various areas are supposed to be, for what various definite integrals are supposed to be, as a way to check your work. So thank you so much for watching today. I wish you all the best and happy integration. Bye.